Hello, my name is Sean and I work for Yellow Tree Environmental. Today's presentation is going to take you through the current small boiler legislation in South Africa. The typical emissions that we expect to see from a variety of fuels when burned on a package boiler, as well as mitigations, in other words, ways in which to reduce one's air pollution. So let's start at the beginning. In 2004, almost 20 years ago, the National Environmental Management Air Quality Act was passed, or NEMAQA for short. This foundational piece of legislation did not have any emissions limits in it, but it paved the way for emissions limits in the future. This piece of legislation said in Section 21 that certain industries in South Africa could be regulated as listed activities, certain appliances could be regulated as controlled emitters, and certain fuels could be regulated. We'll look very briefly at listed activities. The fundamental difference between a listed activity and a controlled emitter is that, in theory, the listed activity listing governs your entire process. So, for example, if you are in the metallurgical industry and you are working with steel, then all of the various appliances in your factory are regulated. However, controlled emitters, on the other hand, regulated specific appliances only, and the most notable of these are small boilers. So let's look at the list of activities. Here we see 68 industries that are regulated. If you conduct one of these activities above a certain threshold, then you need to do two things. Firstly, you need to be licensed. You need an atmospheric emissions license, or AEL for short. And then you need to conduct annual stack sampling, which is where Yellow Tree comes in. It's important to note that as of today's date, which is June 2023, there is legislation in the pipeline that's going to add significantly to these listed activities. But the purpose of today's presentation is not to delve into these, other than to note that boilers are regulated under the listed activities in the combustion installations section. However, it's only boilers larger than 50 megawatts, so we won't deal any further with that in today's presentation, which deals exclusively with smaller boilers in the South African context. So jumping back to the legislation, we see that we have controlled emitters, and the very first of these to be declared was in 2013 when the declaration of a small boiler as a controlled emitter was promulgated. I'm going to take you through these regulations, and this will be the main important part of the presentation. So please stop, screen grab this, get in contact with us, and ask for a copy of this presentation, and particularly this slide. So the very first thing to note is that the legislation regulated boilers between 10 megawatts and 50 megawatts of net heat input. Now that's not the same as the megawatt rating on your boiler nameplate, which typically stipulates the output of the boiler. This pertains to the amount of fuel going into the boiler, the net heat input by design. So 10 to 50 megawatts of net heat input translates into a boiler size of about 14 tons per hour. And if you have one of these boilers, you are forced not to smoke too much. That's called opacity compliance. You are forced to conduct annual emissions testing, and you are forced to comply with the emissions limits. Now, when the legislation was promulgated, they devised two sets of limits. The first was for boilers manufactured after the legislation was passed, and naturally those limits are stricter. And the second set of limits was for boilers that were manufactured before the regulations were passed in November 2013. Why November 2013? Well, that was the date on which the regulations were passed. And so essentially the policymakers said, you know what, we want to be lenient towards industry that already has these boilers installed, but stricter for those industries who are going to be installing boilers in the future, which is a progressive approach to policy making. So over here, we see the limits that pertain to boilers that were manufactured before November 2013. But before I get there, it's important that I do mention that it's the manufacture date of the boiler, not the installation date of the boiler. In other words, you can buy a 1980s boiler, install it at your site, and you are regulated under the older limits. It's the manufacture date of the boiler. So the first thing to note is that there were only two pollutants that were regulated, particulate matter and SO2. Notable in its absence is NOx, which is regulated under the listed activities. And then second to note is that there are different limits for every fuel. There was 5 years of grace, but that has subsequently passed. And then we have the limits for boilers that were manufactured after November 2013, and you'll see that these are stricter. For example, let's take coal, which is the predominant fuel in South Africa, and you'll see that the particulate matter limit is 250 if you operate an older boiler, but 120 if you operate a newer boiler. So without further ado, let's get stuck into those pollutants. When we as Yellow Tree do stack emission sampling, we will measure particulate matter, sulfur dioxide, carbon monoxide, nitric oxide, nitrogen dioxide, which are together bundled together and called NOx. So the question that begs is, which fuel has the highest emissions? And that's always interesting. I love putting this to audiences and gauging the responses. Let's start with particulate matter emissions, in other words, the smoke coming from the fuel. If you operate a coal-fired boiler, it's with good reason that the boiler is called dirty, because you would expect emissions as high as 3,000 milligrams per normal cubic meter. And interestingly, because biomass is a solid fuel, similarly, you would expect high particulate matter emissions. And it's for this reason that coal and biomass boilers are typically equipped with abatement plant, such as multi-cyclones or bag filters. And the purpose of that abatement plant is to arrest the high particulate matter emissions. And so I will get into abatement plant in the subsequent slides. Important to note is that HFO does actually produce a significant amount of particulate matter emissions, and what's even more concerning is that typically HFO-fired boilers are not equipped with multi-cyclones or bag filters, so this is going straight into the environment. And gas is obviously a remarkably clean fuel. Here is a photograph of some of our filters taken from our equipment after doing stack emission sampling. And that filter shows 15 milligrams per normal cubic meter of particulate matter. So that would typically be downstream of a bag filter. That filter shows emissions of 250 milligrams per normal cubic meter, which would be typical of a good functioning multi-cyclone. And that last filter is actually from an HFO-fired boiler and is 1,400 milligrams per normal cubic meter. All right, jumping back to our expected emissions. How do you think each of these fuels is going to compare from the perspective of SO2 emissions, or sulfur dioxide? Well, the answer is that coal produces moderate amounts of SO2 emissions, and I'll explain why on the subsequent slide. HFO produces an enormous amount of SO2 emissions, and gas and biomass are very clean. And the reason for that is because gas and biomass typically don't contain any sulfur. As I mentioned, let's take a look at the sulfur content of various fuels. So South African coal typically has 0.5 to 0.7, or some would say 0.5 to 1% of sulfur in it. That's a moderate amount of sulfur. But HFO has 3.5% sulfur in it. Now, it's important to note, let's just pause here for a second. Diesel has 0.05% sulfur in it. Forgive me for clicking that yellow block. Let me make that go away. Diesel has 0.05% sulfur in it if it's 500 ppm diesel. If it's 50 ppm diesel, then it has only 0.005% sulfur in it, which is very small. So as an interesting exercise, let's convert the number of 3.5% that describes the sulfur content of HFO to a ppm value. Why should we do that? Well, all of us are comfortable with ppm values. We pull up at the service station driving our bakkie, and we ask for 500 ppm or 50 ppm or 10 ppm diesel, depending on how environmentally conscious we are. HFO at 3.5% sulfur has 35,000 ppm of sulfur in it. In my opinion, it's an environmental travesty that we're even allowed to burn HFO in South Africa. But there you have it, all of the sulfur contents of a variety of fuels. There we go. So moving back to our legislation slide, it's important to note that HFO has a sulfur dioxide limit of 3,500, which means that if you are burning HFO and your emissions are likely to be 5,000, you are probably going to contravene the SO2 limit on HFO firing. Now, one clever solution to this is to switch your HFO-fired boiler from HFO firing to firing low sulfur oil, LSO as it's often called, because that only contains 1.5%. I say only, but we have to remember that 1.5% is 15,000 ppm of sulfur, so it's still a very sulfur-heavy fuel, far heavier in fact than coal. And so jumping back to our legislation slide, we will see that if you install an HFO-fired boiler after November 2013, you will be subject to a very strict limit of 500 milligrams per normal cubic meter of SO2. And there's no way that you could meet that limit burning HFO or burning LSO for that matter. So you would have to switch your HFO-fired boiler to burning diesel, for example, or potentially consider installing a coal-fired boiler or another boiler. Alternatively, of course, one could treat the flue gas from the HFO-fired boiler by installing flue gas desulfurization, which I'm not going to go into in this presentation. But what I will say is that flue gas desulfurization is most easily addressed by wet scrubbing, because wet scrubbers spray water and SO2 is highly soluble in water, forming H2SO4. Or you can dose a lime or a particular absorbent that will absorb the SO2. Let's now take a look at the NOx emissions from this variety of fuels that we're looking at. Coal produces moderate NOx emissions, HFO produces very high NOx emissions, and gas and biomass both produce very low NOx emissions. So once again, HFO is the highest offender here. One might ask, how are NOx emissions formed? And the answer is they are formed under conditions of very high temperature and where there's an abundance of nitrogen and oxygen available. So the reason that we have lower NOx emissions when burning gas is because when one combusts gas, there's very little excess air that's placed in the boiler. There just isn't a need for it. Excess air is required when you're burning solid fuels like biomass and coal because of boundary layer theory, whereas when you're burning gas, the gaseous fuel and the oxygen, the air that you're putting in to combust the gas, they mix very well together. So you need very little excess air. Because there's very little excess air, there's also very little extra oxygen available. And so NOx is formed only to the extent shown here. However, when you are burning coal, and to some extent when you're burning HFO as well, you add a lot more excess air. And for that reason, there's a lot more oxygen and nitrogen available. Although you're putting a lot of excess air into a biomass-fired boiler, biomass-fired boilers typically operate at a lower furnace temperature, and NOx is preferentially formed under very high temperatures, 1,000 degrees centigrade and above. And so for that reason, we have less NOx being formed when combusting biomass. Now lastly, although it's not an acute pollutant, I have included CO2 as the final column of our table here. Particulate matter, SO2, and NOx are acute pollutants or criteria pollutants. You'll hear those terms often. That means that they harm humans, animals, and plant life. CO2 does not harm us. In fact, when I go for a jog, I produce CO2. As I breathe and do my work every day, I produce CO2. So it doesn't harm me, but it does have a long-term consequence on the planet in the form of global warming. And so it's important to consider it as well. Now, all of these fuels are fossil fuels, so all of them do release CO2, except for biomass, which is not a fossil fuel. So technically, biomass is carbon neutral. And I'm reluctant to say that because if we go and look at the IPCC codes, we will see that there is some methane and some N2O produced, and that those are CO2 equivalents. And so burning biomass does actually have an environmental impact. It's not entirely carbon neutral, but it's so much more neutral than the other fuels that it's worth just noting it as neutral here. Gas is only medium from a CO2 perspective, and the reason for that is because a gas-fired boiler operates much more efficiently than a coal and HFO-fired boiler. Or coal or HFO-fired boiler. And the reason for that is because, once again, you're putting a lot less excess air into a gas-fired boiler, so the thermal efficiency of a gas-fired boiler is much higher than coal and HFO-fired boilers. Because the thermal efficiency is higher, in order to produce 1 ton of steam, you need less fuel, fundamentally, with gas. And so that's why I would rate gas as medium from a CO2 or global warming perspective. In other words, gas remains a fossil fuel, but it's arguably the best from a global warming perspective. Now let's pause for a second and look at the results going across the table. What we see is that coal does have high PM emissions, but those are often abated in the form of a multi-cyclone or a bag filter. The SO2 and NOx emissions are moderate. HFO has reasonably high PM emissions that are almost never abated, very high SO2 emissions and very high NOx emissions. So HFO is actually our dirtiest fuel out of all four of these fuels. Gas ranks as the cleanest, as you can see, and biomass is carbon neutral, relatively, almost carbon neutral, which is good, but one does need to address the high particulate matter emissions associated with biomass. And this is often done by using an electrostatic precipitator or potentially a bag filter, but those pose a fire risk when they are treating biomass. And so that does lead me on to the next section of the presentation, which is how do we reduce emissions? In South Africa, typically it's particulate matter emissions that we want to reduce, and wet scrubbers are one solution that will take care of particulate matter, but will also address SO2 because SO2 is soluble in water. All the other abatement techniques, electrostatic precipitators, multi-cyclones, and bag filters, will only address particulate matter. And it's very seldom that NOx emissions are addressed in South Africa. So without further ado, let's take a look at the abatement options available to us. The most prolific in South Africa are multi-cyclones. These will pull your particulate matter emissions down to 250 milligrams per normal cubic meter, but will only really arrest particles larger than 5 microns. And unfortunately, they'll break down the larger particles into smaller particles because of the strong frictional forces inside multi-cyclones. And that's not good because smaller particles stay airborne for longer and are the particles that have the biggest impact on human health. These are known as PM2.5 and PM10. PM2.5 is so fine that when breathed in, it goes straight into your lungs, through your lungs, into your bloodstream, and has a significant effect on human health. In fact, it's estimated that 79,500 deaths will be associated with the continued use of Eskom's current fossil fuel-fired fleet during its lifespan. So I think that's just an indication of just how severe these particulate matter emissions can be, particularly the fine PM2.5 and PM10 emissions. So let's take a look at how a multi-cyclone works. Here we see the particulate matter entrained in air entering the multi-cyclone. Multi means several cyclones. The air is swirling as shown by the yellow arrow, but when the air gets to the bottom, it reverses direction and forms a small vortex or spiral and exits out the vortex finder at the top. And the reason for that is because the air has nowhere to go because the bottom of the multi-cyclone is sealed. Let's watch the video one more time. Let's this time look at the particulate matter. It's swirling inside the multi-cyclone, but because the particles occupy a very small volume, they are able to enter the bottom of the multi-cyclone without displacing much air. They're then collected on a seal or a flap, which is then closed, and then it's discharged out the bottom. And that's how a multi-cyclone works. Here's a lovely photograph of a multi-cyclone connected to a stack and another multi-cyclone connected to a common stack. At the bottom over here, you will see the ID or induced draft fans. Another great picture, shown a little bit closer up. Here we have the dirty flue gas exiting from the boiler as shown by my mouse. It would then spiral through multi-cyclones or through cyclones housed in this multi-cyclone casing. The particulate matter would be discharged through this trickle valve or dual flap system, which in this case is automated by a little motor and collected in the trolley at the bottom, while the cleaned gases would exit through the ID fan and out the chimney stack. However, it must be noted that while these gases have been cleaned from 3,000 milligrams per normal cubic meter to 250 milligrams per normal cubic meter, 250 is still a large concentration of particulate matter, especially when one considers that the majority of that will be PM2.5 and PM10. Now, there are a number of problems associated with multi-cyclones. The first is that the cyclones are housed inside a closed body, and so they're often not inspected. We've done a number of multi-cyclone inspections online using a specialized camera rig, and this video will reveal that a lot of the cyclones inside the multi-cyclones are actually completely eroded. Those ones are in good condition, but those are in poor. And those ones are completely disintegrated. And those ones are in good condition. So as you can see, multi-cyclones require a lot of maintenance and are often not seen until we come and do stack emission sampling and measure very high particulate matter emissions, and then questions are asked around the condition of the multi-cyclones. Another common problem is that those two flaps at the bottom that are supposed to maintain a seal often become stuck open or erode entirely because the particulate matter is very abrasive. One of the solutions is to use a Benox plate at the bottom instead of a regular mild steel plate, but even then, regular maintenance needs to be done and inspections need to be done. So what happens if the seal is broken? Well, this video answers that question. Here we have the multi-cyclone operating normally. This flap opens but becomes stuck open, and then the bottom flap opens and also becomes stuck open, and then we have air being drawn in from outside because the ID fan is downstream of the multi-cyclone, and that just destroys the vortex inside the cyclone, meaning that all the particulate matter essentially exits out the stack, and the multi-cyclone is really just bypassed. The next problem is blockage of the spinner vanes. So here we can see the individual cyclones that have been pulled out of a multi-cyclone. The cyclones are in good condition, so all looks good. However, if we look from the top, we will see that the spinner vanes over here, which create that vortex swirling motion inside each cyclone, are completely blocked with particulate matter. This is often an unseen problem, and the result of this is shown in the following video. Here we have particulate matter entering. The first cyclone is working well, but the latter two are beginning to block up. And what happens is that because there's a blockage over here, these two cyclones form an easy exit path for the air. So the air is no longer forced to spiral upwards and reverse its path. It has a short circuit out these remaining two cyclones. And so this greatly limits the efficiency of a multi-cyclone. Let's watch that video one more time. Here we have the air swirling. Normally it would reverse upwards and exit out this vortex finder, but instead it has an easy exit path. The fourth problem with multi-cyclones, which I've mentioned already, is that multi-cyclones subject particles to very strong forces. And this results in particles breaking down into even smaller particles. This slide shows us, without going into too much technical detail, that ash is very, very friable. And that means that it breaks down easily. So, when subjected to the strong forces inside a multi-cyclone, big particles become smaller particles and escape out the multi-cyclone. So essentially, multi-cyclones create a new air pollution problem that didn't exist. You've got particulate matter coming off the back end of a boiler, and some of those particles are really large and would be of no harm to the environment and would naturally fall out of the air, but instead, those big particles are broken into finer particles inside the multi-cyclone, are then not captured by the multi-cyclone, and exit as far more dangerous PM2.5 and PM10. This slide is intriguing because it shows the size of a PM10 particle. 10 means 10 microns. 5 PM10 particles would fit into the width of one human hair. 20, would it be? 5 times 4? Yeah. 20 PM2.5 particles would fit into the width of one human hair and are shown here as these little red dots. PM2.5 is tiny. And it's no wonder that it enters the human lungs and enters directly into the bloodstream. That can be particularly dangerous if the PM contains heavy metals. Now, the fifth problem with multi-cyclones is their varying performance. This graph tells the story. Over here on the x-axis we have the gas flow rate, and on the y-axis we have the efficiency of a multi-cyclone. And we see that the efficiency is an actual fact of function of the flow rate. And this means that if your boiler is just idling along, well, your multi-cyclone won't be very effective because you'll be operating on this part of the graph. And if you are running your boiler really hard and pumping too much excess air through the boiler, which is a common problem in South Africa, boiler operators will pump excess air through the boiler to clean up the emissions. But that reduces the efficiency of the boiler in terms of its thermal efficiency, but it also reduces the effectiveness of the multi-cyclone. And then you'd be operating on this part of the curve over here, with diminishing effectiveness of the multi-cyclone. And so the variable efficiency or performance of a multi-cyclone is one of its drawbacks. One of the other drawbacks of a multi-cyclone is because it's a completely sealed unit, it often does not receive the attention that it should. And this video tells a wonderful story in that regard. Here's a multi-cyclone that I opened up, and as you can see, the whole unit is filled with particulate matter. That means that this multi-cyclone is essentially bypassed and filled all the way up to the top and is not performing any separation functions. So that wraps up multi-cyclones. Let's look at another technology, bag filters. Bag filters represent the Rolls-Royce solution. They will pull particulate matter emissions all the way down to 15 milligrams per normal cubic meter by way of concentration, and they will arrest all of the smallest particles. Most of the PM10 and the PM2.5 will be caught. In fact, it's only particles that are smaller than 0.2 microns that won't be captured. This makes bag filters the ideal solution when one is installing a new boiler that was manufactured after November 2013, when one has to meet the strict limit of 120 milligrams per normal cubic meter. Multi-cyclones will only make it possible to meet the limit of 250, and even then, they'll struggle to do so consistently, whereas bag filters will pull the emissions down to 15 milligrams per normal cubic meter consistently. Manufacturers of bag filters will guarantee emissions to be below 50 milligrams per normal cubic meter, which is excellent, and as I mentioned, we continuously measure about 15 or 20. So how does a bag filter work? Well, this video will answer that question. Here we have the dirty gas entering the multi-cyclone. It passes up through an array of bags and leaves the top of the multi-cyclone as cleaned air. Sorry, multi-cyclone, the top of the bag filter as cleaned air. The particles build up on the bags, and as they build up, air struggles to make its way through the bags, leading to a greater pressure drop over the bag filter. As a result, we have a plenum of compressed air on the side of the bag filter that injects compressed air into the bags, cleaning them while the bag filter is online. And it's amazing that this unit can clean itself while the bag filter is online. That's often called a jet pulse bag filter. There's a photograph of two bag filters installed side by side serving a common stack, and these were installed downstream of two 10-ton per hour coal-fired boilers. What's important to note is just how large these bag filters are. Multi-cyclones are probably a third of the size. There is another lovely photo of a bag filter installed on an 8-ton per hour coal-fired boiler. And what's important to note is there's actually a little multi-cyclone upstream of this bag filter. That is sometimes common practice, and that's to put a multi-cyclone directly downstream of the boiler to arrest the majority of the particulate matter, therefore preserving or saving the bags, in inverted commas. However, many manufacturers of bag filters will tell you that the cake that builds up on the bag filters is actually really helpful in filtering. And so a lot of manufacturers will recommend that the bag filter be installed directly downstream of the coal-fired boiler. Once again, an important reminder that a bag filter is not suitable for a biomass-fired boiler, in other words, a boiler fired on wood, because often the particulate matter from wood is very light and fibrous, and so it's carried out and remains entrained in the air, and therefore makes contact with the bags while it's still burning. And that leads to a fire in the bag filter and is not a good solution. So that wraps up bag filters. There is one more technology that is far less common in South Africa, but still very useful, and that is ESP, or electrostatic precipitator technology. It arrests most of the small particles, but it's not as effective as a bag filter. And the nice thing is the concentration that it will arrest down to can be used as specified. And the reason for this is because there is free airflow through the electrostatic precipitator. So you can simply make the electrostatic precipitator bigger and put more electrically charged plates in the precipitator to catch the particles, and you will pull the particulate matter concentration down to a lower value. If you're on a tighter budget, you might not pull it down to as low a value, and you might design a smaller unit. However, with bag filters, you don't have that luxury. The unit is sized based on the airflow through it. And it's based on that airflow that you have to size it. And so you're stuck with a really good emissions concentration of 15 milligrams per normal cubic meter. You can't say, well, you know what, I would like to pull my emissions only down to 120 milligrams, which is the limit for new coal-fired boilers that were installed after November 2013. So I'm going to install a smaller bag filter. Well, that wouldn't cut it because you'd have a very high pressure drop over that bag filter due to the bags, and it wouldn't operate as required. So bag filters are sized based on pressure drop, whereas electrostatic precipitators can be sized based on the concentration of particulate matter that you desire. Here's a lovely photograph of two electrostatic precipitators serving two biomass wood-fired boilers. ESPs are suitable for wood firing instead of bag filters because they're not prone to burning down when small embers, small particles that are still burning, make contact with the plates. And lastly, one more photo of an enormous electrostatic precipitator, which is arresting particulate matter downstream of an HFO-fired installation in South Africa. Interestingly, this stack was one of the largest polluters in Cape Town, South Africa, until this electrostatic precipitator was installed. So it has served very effectively to reduce PM emissions. So that brings me to an end of our presentation. Yellow Tree is operational in the air pollution space in South Africa. Our main service offering is stack emission sampling, as you can see. One of our scientists active over here sampling a stack for PM, SOx and NOx. But we also take care of atmospheric emissions license applications, carbon tax, dispersion modeling, fence line monitoring for BTEX, benzene, toluene, ethyl benzene, and xylene, as well as a variety of other air pollution offerings. So please do reach out to us. We would love to chat to you. There are a couple of other photos remaining, which I'll take you through quickly. That was us serving a large power station in South Africa. Some of our scientists on site. A lovely photograph of our equipment in action, actually sampling halides, HCl, HF, and ammonia. A photograph of us in Swaziland on a very tall stack. And we serve the process industries as well. Thanks so much for taking the time to watch this presentation pertaining to boiler emissions in South Africa. I hope that you've learned a lot, and don't hesitate to get in contact.